EN 1990 covers the basis of structural design, and you'll need to use it in conjunction with other Eurocodes. So, to get the partial safety factors for actions and combinations of action for the verification of both ultimate and serviceability limit states, we will need to refer to EN 1990. The ultimate limit states are to do with the failure of the structure. Ultimate limit state checks are needed to verify the safety of the structure, while serviceability limit state corresponds to conditions in use of the structure. The limit state could be related to cracking or deformation. In EN 1990 there are three important ULS checks. Equilibrium, loss of static equilibrium of the structure. Equilibrium is used to verify the stability of the structure or parts of it, for example, against overturning, sliding or uplift. When considering a limit state of static equilibrium of the structure, the verification will need to ensure that the design value of the effect of destabilizing actions is equal or less than the design value of the effect of stabilizing actions. Structural, internal failure or excessive deformation of the structure or structural members, including footings, piles, basement walls, etc., where the strength of construction materials of the structure governs. Geotechnical, failure or excessive deformation of the ground where the strengths of soil or rock are significant in providing resistance. When considering a limit state of rupture or excessive deformation of a section, member or connection, STR for the superstructure and the STR component of STR, GEO for the structural design of the foundations, the verification will need to ensure that the design value of the effective actions, such as moment, is equal or less than the design value of the corresponding resistance. Actions may be permanent, for example self-weight of structure, fittings and fixed equipment, or variable, for example, weight of occupants, wind and snow loads. A variable action can be leading or non-leading. A variable action has four representative values to be used for the appropriate design situations for the ultimate or serviceability limit state verifications. These are the characteristic variable action is represented by QK, combination value by psi0 QK, and the frequent value by psi1 QK, and quasi-permanent value by psi2 QK. We have the different site combination factors for different load situations, which we can get these factors from the table UK National Annex, A11. When we need to consider combinations actions, there are two options that we have. First option is to use equation 610. Alternatively, we can use less favorable results of equations 610A and 610B. Here we have the first option, and this is equation 610. We have the permanent load factor, gamma G, times the permanent action Gk, plus leading variable action, times the partial factor gamma Q. The leading variable action creates the most unfavorable effect. And sometimes when it's not obvious we need to consider each variable in turn. And then at the end here we have any other variable actions times a partial factor gamma Q, times combination factor psi0. Here's the second option that we have. We have equations 610A and 610B, we need to check the least favorable of these two. So, equation 610A is similar to 610B, except we have extra combination factor applied to the leading variable action. Equation 610B is the same as equation 610, except that we have this term xi, which is a reduction factor, and the value of xi is taken from the National Annex is 0.925. For unfavorable actions, a partial safety factor for permanent actions, gamma G is 1.35. And for variable actions gamma Q is 1.5. For favorable actions, permanent actions, a factor is 1, and the variable actions, the factor is 0. An unfavorable action is the one that helps, for example, the foundation to fail, when the vertical load is downwards. There may be some situations where an action is favorable, such as an upwards load, which helps to stop the foundation failing. A permanent action has a partial factor of 1, since to make the design value of the action higher would not be conservative. A favorable variable action has a partial factor of 0, because it may not always be there. In accordance with Table National Annex A11, values of psi factors for building, psi naught is 0.7 for most imposed loads and 0.5 for wind actions. First of all, we have option 1, we're going to be using the equation 610. So, we have a partial safety factor for the permanent load, gamma g, and that's 1.35. The partial factor for the leading variable action, gamma q, and that's 1.5, and for the other variable actions, we need to multiply partial safety factor by the combination factor. If we take the floor imposed load as a leading variable, we need to multiply the other variable loads. It should be the wind load psi factor, which is 0.5. We get 1.35 times the permanent action, plus 1.5 times leading variable load, which is the floor imposed load, plus 0.75 times other variable loads, which is the wind load. On the other hand, if you took the wind of the leading variable load, then we would multiply the other variable loads by psi factor for the floor imposed load, which is 0.7. We get 1.35 times the permanent action, plus 1.5 times leading variable load, which is the wind load, plus 1.05 times the other variable load, which is the floor imposed load. So that's how we use equation 610. If we want to use the second option, we have to check both equations 610a and 610b. Here's equation 610a. Again, we have partial factor gamma g for permanent action, that's 1.35. And here, both the leading and other variable loads, multiplied by psi naught and gamma q factors. For the floor imposed load, that is 1.5 times 0.7, for the wind load, that's 1.5 times 0.5. We get 1.35 times the permanent action, plus 1.05 times floor imposed load, plus 0.75 times the wind load. Here's the equation 610b. This is a bit more complicated, because we don't know what the leading variable is. So, we need to consider all situations. First of all, we're checking the imposed load is a leading variable load. The other variable load is the wind load. We use the psi factor of 0.5. We also need to multiply by gamma g, partial factor by xi, which is 0.925. We get 1.25 times a permanent action, plus 1.5 times leading variable load, which is the imposed load, plus 0.75 times other variable load, which is the wind load. Next, we'll consider two other possible situations. Now if we take the wind as the variable leading load, we will get 1.25 times the permanent action, plus 1.5 times the leading variable load, which is the wind load, plus 1.05 times other variable load, which is the imposed load. Now if we assume that there is no leading variable, then we treat both the imposed and the wind load as other variables. So, we multiply both by psi naught factors, we get 1.25 times the permanent action, plus 1.05 times the imposed load, plus 0.75 times the wind load. Now, you can use either equation 610, or we could use option 2, which takes the least favorable results from equation 610a and 610b. Let's now take a simple example. Consider the forest fire observation tower with wind blowing on the side. To obtain the maximum, compressive design load in the support leg at B, 3 load combinations should be checked, and the larger value used in subsequent design calculations. Load case number 1 with the floor load is the leading variable action. 1.35 times dead load, plus 1.5 floor load, plus 0.7 times 1.5 roof load, plus 0.5 times 1.5 wind load. Load case number 2 with the roof load is the leading variable action. 1.35 times dead load, plus 0.7 times 1.5 floor load, plus 1.5 roof load, plus 0.5 times 1.5 wind load. Load case number 3 with the wind load is the leading variable action. 1.35 times dead load, plus 0.7 times 1.5 floor load, plus 0.7 times 1.5 roof load, plus 1.5 wind load. Next, to obtain the maximum tensile design load in the support leg at A, we must minimize the effect of permanent and variable actions by using the following combination. Dead load plus 1.5 wind load. In other words, the tower is much more likely to blow over when the variable floor and roof loads are zero. For such overall stability checks, the value of gamma G is reduced further to 0.9. For large and complex structures, the theoretical number of possible load combinations can be formidable. However, the experienced designer quickly learns which ones are the most critical. Finally, when checking structures against serviceability limit states, such as deflection or cracking, the loads are usually used unfactored.